Alright, so I'm just going to get right into it. We talked a little bit about the differential equation, or system of differential equations, ux equals a of x, y, u, and uy equals b of x, y, u. And we talked about how we could solve those by integrating them one at a time. And then we discovered that because the mixed partials commute, we had to have a certain hidden condition relating the a and b in order that the system actually have a solution. So what I'm going to try to do now is to describe how we can look at that in terms of differential forms and such. And so the basic notion here is to use a space called jet space. So we're going to introduce this notion of jet space. Okay, so to start with here in this first little lecture, we're going to talk about basically J1. Now, this is going to be J1, and let's see here, well, I'll talk about it more generality next time, but here we're just talking, here's a typical point in J1 has something like this. It has points x, y, u, and then P and Q are our typical notation here, and these are just real numbers. All right. So this is the first jet space built over for maps from R2 to R. Now you're like, well, that's just R5. Well, that's true. It is just R5. But then the question then, of course, is how does that relate to other things, differential equations in particular, and central to that notion is this idea that we can talk about the lift of a function u of xy, right? Now, lift of u xy, so that would be something like this. So this would go to the point x, y, u, and that's of course u of xy, and then ux, okay, at the point xy, it's kind of getting annoying to write that, and then uy of xy. So, given a function, right, from R2 to R, we can naturally define this point in R5 that corresponds to the function, so-called lift. And so ultimately what we want to do is think about this being the solution to that system up there and see, what do those solutions look like up on jet space, and how do we encode this system of differential equations, let's call it, give it a name, I don't know, Quentin. There we go. How do you put Quentin up on jet space, I guess, is the question. And so there's two, let's go. Basically there's two things we need. We need this, first of all, we define this so-called contact form. So the contact form is theta. Now theta is going to be a differential one form up on J1, and so it's du minus PDX minus QDY. All right. So, and we're going to use this to basically make things look like lifts upstairs up in the jet space. All right. And then there's also this contact form. There's also an independence condition. In the independence condition, omega, which will just be rather boring, it will be dx wedge dy. Now, this being non-zero essentially means that x and y are independent, right? Now, but these are forms up on J1. And then, so these are in the first jet space, all right? So then consider, suppose you have a surface in jet space, all right? Let's say, and typical notation for that, something like this. We'll let I be the including map, so I such that S is included into jet space, all right? And that's a surface, meaning it's two-dimensional, right? Such that what? Such that the pullback of this independence condition is not equal to 0. Then, like I said, then it follows that dx and dy are linearly independent one-forms on S. In other words, we can use x and y as coordinates on such a surface in jet space. All right. On the other hand, if we consider what it means, suppose you look at the contact form, the theta, right? What does it mean for theta to pull back to 0? What would that give us? That's the idea here. Theta, under this inclusion map again, theta pullback pullback of theta would be what? So this is the pullback of du minus PDX minus QDY, all right? That's equal to 0. Suppose we make that condition. Well, if we can use x and y as coordinates, then we're just going to abuse notation a little bit. Say the pullback of dx is dx again, and the pullback of dy is dy again. All right, so not too bad of an abuse of notation. And so what this then says is that I pull back du, right, is equal to PDX plus QDY, with the understanding that here P and Q evaluated on the surface, all right? So you're composing P and Q with the inclusion map, all right? Now, on the flip side of things, du is the exterior derivative of the u function, and if u is just a function of x and y, because after all, we're on the surface, and x and y are they suffice to give coordinates on surface, so u is a function of x and y if it's a function on surface. Anyway, so du, of course, is just also what? So this is also equal to, over here, right? I pull back of ux dx plus uy dy. And that is just ux dx plus uy dy under our current abusive notation. And so, therefore, you see that the condition that the pullback of the contact form is 0 is really just equivalent to saying what? It's really just equivalent to saying that this thing, again, dx and dy are linearly independent, so we can equate their coefficients. Ux is equal to p, and q is uy. So there you have it. Let me just summarize everything here. Or sure, I'll summarize it over down here. Well, hopefully you got that by now. I'm going to erase it. Let's see here. So I pull back to 0. What does this mean? Contact form pulling back to 0 is basically giving us that ux is equal to p and uy is equal to q. All right? Now, in other words, if we have a surface, so if we have S with both of these things, right? If we have a surface such that the pullback of the independence condition omega is not equal to 0, and the pullback of theta is equal to 0, then it follows that that this S basically has lifts of functions of x and y, right? Now, nothing so far about the differential equation. I mean, nothing about Quentin so far. This condition so far, the independence form and the contact form, that just forces on the jet space us to be looking at a surface where we have independence of x and y, and the meaning of p and q is that they're actually partial derivatives of the dependent variable. u with respect to the independent variables x and y. Now, enters the threefold. So next we look at a threefold, or a three-dimensional submanifold, and the notation used in Cartan for beginners, which I'm following, of course, is that J is an inclusion of this sigma into the first jet space. All right, and then if you look at, and what's this? This is going to be defined by. What's it defined by? Very simple. Now we're gonna, use Quentin here. Basically, ux, since ux is p, well, we use p equals to a of xyu, and q is equal to b of xyu. Now you notice that these are algebraic conditions. So we created a differential equation for an algebraic equation on jet space. You should maybe recognize this from your differential equations course where we introduce new variables. This is a common technique, really, just the generalization of the reduction of order idea. And anyway, so that said, if we look at a surface, which is basically, you have I, which takes the surface and includes it inside this guy, and then that, of course, goes into the jet space. So in other words, this is going to be a surface with the independence condition and the contact form, and then that's inside this, which has the defining, algebraic conditions. Then that will give us a special kind of surface in the jet space, which actually does correspond to the differential equation. All right, so let's see how that goes. Let's see here. So just a couple calculations. What is? I need to erase some of this. Well, I guess I can't. So what's d theta then? Let's see if I can get this. So d theta, remember theta was, so it's d of du minus PDX minus q dy, but that of course will be minus dp wedge dx minus dq wedge dy, right? And so if we pull back d theta under j, right, then what happens? We get what? Well, p is equal to what? Basically, what equations define? I mean, how do we do pullback? Essentially, just what defines the sigma is p equals to a, right? So if I do dp where p is equal to a, that's really just what? That's really just minus ax dx plus ay dy plus au du wedge dx minus bx dx plus b, there's minus outside, by dy plus bu du wedge dy. All right, so what I'm doing, of course, is just, what does pullback under J mean? It means you use the equations that define the sigma, which are p equals to a and q equals to b. And, all right, so what happens there then is, what? Well, of course, the dx wedge dx we can ignore, and we're just left with like 4 terms here, right? And those 4 terms are the ones we found last class. Those are exactly the 4 terms that were interesting for, so like this one, and this one, and that one. Those are the ones that don't wedge to 0. And what do we got? Well, we got j pullback d theta is equal to what? Let's see here. And if you look at it, fine. No, I don't have a lot of board space. Let me just get to it. So dy wedge dx, I'm going to switch that around. I've got minus ay. I'll put a big parenthesis out here, and then I'm going to have dx wedge dy. All right, I'm going to think about this. So this term, dy wedge dx goes to dx wedge dy. I got a minus ay. Now I've got du wedge dx, right? So which would give me what? Well, I guess it would just give me, well, what do I want to say here? I guess I got to pull back to I to do more, but I'll find just an intermediate step. Plus a, u, oh curses. I guess I have to, fine. Then this one, what else here? Minus bx, right? Minus bx, all right, great. Dx wedge dy. And then I've still got these other terms, right? Plus au, du wedge dx, and then plus the bu, du wedge dy. Now if I pull back that, so at this point, I mean, we started with, let me just kind of draw a schematic of what's going on here, thinking about pulling back things. Started with d theta here, right? And then this is the j map, so that then this is j pullback, d theta lives here, right? And then I can pull back that one more time, like this, right? Because this is the I map. And so I can pull back over there. I can look at I, pull back j, pull back d theta. This is just a lot of notation for a simple idea, which is that now we're going to, what? We're going to look at u as a function of x and y, basically. So the du then becomes what? Well, the du becomes, now at the next level, du will become like ux dx plus uy dy. Dx wedge dx goes to 0, so what you're going to get is you get like minus ay minus bx, and let's see here, from the du we pick up au, so minus au uy. Now the reason it's a minus is because I would have dy wedge dx, and to flip it I get a minus. Now over here in contrast I'm going to pick up plus b sub u, and when I pull back the u becomes, what is it? It's ux dx, so it's ux, and then there's dx wedge dy out here. Okay, but again, where are we? You know, this is sort of, this isn't, keep in mind that we're imposing the conditions for the surface and for the threefold. So we're looking at surface inside the threefold. We have both the conditions p equals a and q equals to b, and we also have the condition that the contact form pulls back to 0 and the independence condition is non-zero. Okay, so the contact form pulling back to 0 means that ux is equal to p and uy is equal to q, right? So p and q, but then again, p and q are not p and q anymore, they're a and b respective. And so we get, excuse me, minus ay minus bx minus a sub u. Uy is q, but q is b. And then plus bu, ux, but ux is not. Ux is p, but p is a, because we're in our current context, okay. All right, so there you have it. That thing I just got in the parentheses here, right here, this quantity, partial derivative of a with respect to y, negative, minus partial derivative of b with respect to x, minus partial derivative of a with respect to u times b, plus the partial derivative of b with respect to u times a. All of that vanishing was the necessary condition for us to have the partial derivatives commute in the solution that we constructed by step-by-step integration of Quentin. Now, in other words, we find then that the condition, the hidden compatibility condition we found before, we can impose it by simply insisting that, if you will, the pullback of, basically the pullback. I mean, if you'll just allow me a slight, well, a little more than slight, a kind of a gross abuse of notation, let's just call this thing d theta. So essentially we need d theta is equal to 0, is essentially that condition. All right. In terms of the identifications we've made here. Now, So I suppose that would mean if you look at the ideal that is built from theta and j, it's a differential ideal, and it is, what's the word? Frobenius, I suppose. I'll try to talk more about that more systematically in the next time. But, I mean, you already see anyway, at least, that this differential form being 0 in the context, right, of these conditions corresponds to that naturally encoding that compatibility condition. I think that's really kind of striking the first time you see it. Now, I don't think that we have currently put these things on a very solid theoretical ground, and I'm still trying to personally come to terms with exactly how the Frobenius theorem theory interfaces with what we're currently doing. And anyway, hopefully I'll make a little bit more sense of that next time around. And I think I'm going to stop there for now. Thanks.